All right, let's do some applications of partial derivatives. Okay, tangent lines, rate of change, and applications. So I keep talking about functions of one variable, one independent variable to help us think about where we came from and how we're kind of just extending this into a higher dimension. But for a function of one variable, we can find a tangent line, okay, to the curve at a point P, right? We've done that quite a bit in the past. But if we extend that out into another dimension, functions of two independent variables, there's going to be a tangent plane that touches the surface at a point P. So that's this image down here that I have, just a depiction of a tangent plane that touches the surface at a point P. So in any particular direction, there will only be one tangent line at P. And we can use partial derivatives to find individual tangent lines that would all be within the tangent plane that indicate the slope of the surface in the X and Y directions. Okay, but unfortunately, and I know that you're terribly disappointed, but finding tangent planes and tangent lines in 3 space is beyond the scope of this course. So we're not going to be dealing with tangent lines and tangent planes with multivariables, but I wanted to just mention it because it is definitely a curiosity and something that we could just go absolutely crazy talking about. Okay, really awesome topic there, but yeah, we're not going to be focusing on that one. What I want to focus more is rate of change. Okay, and I have several examples that we're going to do in a couple more videos for rate of change. So let's talk about the rate of change and then we'll do example 5. So recall that the derivative of a function y equals f of x gives the rate of change of y with respect to x. Okay, so similarly, if z equals f of x comma y, then the partial derivative of f with respect to x, okay, remember that notation, that gives the rate of change of z, or we could say it gives the rate of change of f with respect to x if y is held constant. So I wanted to break that down in a couple of different scenarios because it is a little bit tricky when we want to try to think about what does it mean when we're thinking about the rate of change? Because it does kind of go back to when we think about slope or what like a single unit rate of change would be. So I want to really talk about that and outline the 2 different scenarios that we need to talk about. Because when we're working on these problems, finding the number or finding the derivative is usually not too hard, but interpreting is the hard part. So I really want to break that down right here. And that's the whole point of partial derivatives, is being able to find some really interesting interpretations when there's multiple variables involved. So if z equals f of x comma y, then the partial derivative of f with respect to x evaluated at a comma b, okay, so at some numbers, that represents the change in f, or the change in z if you want, when x changes by 1 unit, from x equals a to x equals a plus 1. So that's the tricky part in my opinion, and I'll talk about that in a little bit more detail. Okay, and then so that's x is the variable, and so we're talking about the rate of change of x as x increases by 1 unit. Okay, and then y remains constant. Okay, so remember when we're doing partial derivatives with respect to x, that means we're just making the other variable constant. So for that part, the other variable being constant evaluated at that number, I don't think that that's too bad, but this is definitely tricky when we're thinking about the rate of change from the other variable. We want to think about it in terms of a change in 1 unit. And similarly, if we've got the same function, but we do the partial derivative with respect to y, evaluated at a comma b, that's going to represent the change in f when y changes by 1 unit. Okay, so we go from b to b plus 1, and then x remains constant at a. Okay, and then so it's a little bit tricky, but the way we want to think about this as that change in 1 unit, if we went back to the old days and we thought about like, okay, if you found the derivative evaluated at some number, and suppose that the derivative came out like 3. Remember that 3 would mean that that's a rate of change, that's a slope. And when we think of slope, it's always like per unit increase in the variable. Okay, so per 1 unit increase in the variable, the overall function would increase by 3. So that's kind of the same idea here, is we really want to just think about per unit increase, okay? And that's the hardest part when we're going to the interpret part of the problem, because we have to be very, very careful about what all of the variables represent in the context of the problem. Okay, so I'm definitely going to be writing a sentence to answer the problem, to answer this when it says interpret. Okay, so let's try example 5 here. Here we go. Suppose that the temperature of water at the point on a river where a nuclear power plant discharges its hot water waste is approximated by T, okay, capital T for the temperature, x comma y equals 2x plus 5y plus xy minus 40, where x represents the temperature of the river water before it reaches the power plant, and y is the number of megawatts in hundreds of electricity being produced by the plant. Okay, so lots of variables involved. This function, T, capital T, that represents the temperature of the water right at the point where the power plant is discharging its waste. So we want to keep that in mind. The overall function is talking about the temperature of the water right at the plant. Okay, X represents the temperature before the water reaches the plant, and Y is pretty much how much energy is being produced by the plant at that moment. Okay, so lots to absorb right there, and we're definitely going to write a sentence to, when we want to answer this question. So we've got part A, we're going to do the partial with respect to x, and part B, we're going to do the partial with respect to y. Notice that it's evaluated at 9, 5 both times, but we have vastly different interpretations. Okay, so first things first, let's just find the partial derivative in general. Okay, and so like I said, the find part is not too bad. It's the interpret part that's a little bit tricky. So first things first, let's find the partial derivative with respect to x, just in general. Okay, without plugging in the 9 and the 5 yet. Okay, so x is the variable. So the derivative of 2x is 2. Plus y is a constant. So the derivative of 5y is 0. Okay, plus xy. So the variable is x right now, and y is being held as a constant. So we want to do constant times x. The derivative of that is the constant. Okay, and then the derivative of 40, always a constant. Okay, so that's just 0. And so we get 2 plus y. Okay, so that is the derivative with respect to x. Now let's go ahead and plug it in. We want t sub x evaluated at 9, 5. Okay, so plugging in 9 for x, there's no x to plug in, so that doesn't matter. 5 gets plugged in for y, so we have 2 plus 5 equals 7. Okay, so like I said, the find part is pretty easy. The interpret part is the hard part. So here's the hard part, the interpret, and I'm going to make a sentence out of it. What did this capital T function represent? So that's this 7. Okay, this is going to represent the change in what? The temperature right at the point in the river where the nuclear power plant discharges its hot water. Okay, so this 7 is representing an increase in the temperature, but we want to write this down very, very specifically. Okay, so we want to write this out. 7 is the approximate change in temperature. Since that's a positive number, I would assume that we have an increase in temperature, which should make sense. Okay, the power plant is probably increasing the temperature of the river. So 7 is the approximate change in temperature of the output water. Okay, so at the point right as it's passing the plant, this is how much the water increased in temperature. If input water if input water temperature changes by 1 degree, and here's the tricky part, the 9 right there, we're doing X is the variable. So F, and I'm going back to this little statement here because we've got a T function, so the temperature, when X changes by 1 unit. So we have X representing the temperature of the river water before it reaches the power plant. So if the input water temperature changes by 1 degree from X equals 9 to X equals 9 plus 1, which is 10. So if we have that the input water temperature changes by that 1 degree, and so this is where I really want to focus on these, we're plugging in A right here, but we're plugging in 9 in this case. We're changing from A to A plus 1. So we're changing from 9 to 9 plus 1, and that equals 10. Okay, and while what? The other variable, while y remains constant at, and we plugged in 5 for y, but what does that actually mean? I'll put that in parentheses, 500, because y is the number of megawatts in hundreds. So let's write that down. Y remains constant at 5, so that's 500 megawatts of electricity produced. So that is the interpretation. And I think I'll put a degree symbol on there. 7 degrees is the approximate change in temperature of the output water if input water temperature changes by 1 degree from X equals 9 to X equals 9 plus 1 equals 10, while we leave the power plant energy production constant at 500 megawatts. Okay? So it's like we've got this water increase being dumped in there. 7 degrees is the overall change after it passes the power plant. All right, so a little bit tricky there. Let's try this one where we're going to do the partial derivative with respect to y. Okay, so first things first, we want to do the partial with respect to y. So going back to the original function, 2x, this time x is constant, so 0 plus 5y, okay, derivative of 5y is 5, plus xy, so this time the x is constant, so constant times y, the derivative is just the constant, and then minus 40 is still derivative 0. Okay, and so just so I don't run out of room, because I do need some space to write my sentence, if we do the partial of t with respect to y evaluated at 9, 5, 9 goes in for x, 5 goes in for y. So there's no y to plug in, so we just do 5 plus the x, which is 9, and so we get 14. Okay, easy part is over, right? The find part is easy. Let's talk about the interpret. Okay, so again, this overall function is talking about a change in the temperature as it goes past the power plant, right? A point on the river right as it goes past the power plant. So what did we just do? We let x be constant, and we found a rate of change as the y value went from 5 to 6. Okay, like I said, when y changes by 1 unit, from b to b plus 1. Okay, so looking at this one, we're changing from 5 to 6. Okay, so Let's write this out. 14 is the approximate change in temperature, okay, of that river as it passes the power plant, resulting from a 1 unit increase in production of electricity. Okay, because this time we're letting Y be the thing that's changing. And like I said up here, this is the tricky part. A 1 unit increase in whatever the Y variable was from that number to that number plus 1. Okay, so 1 unit increase in production of electricity. Okay, that's from Y equals, so starting at 5 to Y equals 5 plus 1 equals 6. Okay, and it's important to understand, remember that Y variable, Y was the number of megawatts in hundreds. So I want to put that in parentheses as well. From Y equals 5 to Y equals 6. Okay, so that's from 500 to 600 megawatts. Okay, while, okay, the input water temperature okay, the X variable remains, and I'm gonna have to write it down here, constant at, and what do we do? 9 at 9 degrees. Okay, so yeah, multiple variables involved. Very important to read it very carefully and analyze which variable you're taking the derivative with respect to. And then we always want to think about it's that 1 unit increase. Okay, and then be able to really comb through the paragraph and be very careful about what all of the variables represent. Okay, so incredibly powerful application here. We can analyze all kinds of different perspectives of a certain type of situation, depending on which variables we want to focus on. Okay, very, very interesting, very, very cool stuff. And yeah, I agree. The interpret part of it is definitely the most challenging part. Okay, so I'll make a separate video to pick up on example 6.